Now, let's look at a different situation. Let's look at a situation where instead of a mass and a gravitational force, we have a charge and an electric force. And let's look at, let's erase some of this. Remember last time we talked about a capacitor, and we said that inside a capacitor we have, if we're close enough, if the plates are large enough and the gap between them is small enough, we can make a situation where we have a uniform electric field. Okay, so that's what I'm doing here. I have two plates, two disks that are parallel to each other, and they're very long, so these extend upward. And this separation between them is small compared to their size. Okay, so then inside I have an electric field pointing in this direction, and it's uniform. So it's just a constant electric field. And I have a positive charge that enters into this inside this gap of this capacitor. So here's a question. You have a proton entering a capacitor. So let's say we even cut a little hole out of this so we can shoot the proton inside. And it enters into the capacitor and it has some initial speed. And it's moving from A to B. Okay? Which is going to be true for the kinetic energy and the potential energy of this entire system? System is the capacitor plus the proton. System is the capacitor plus the proton. That's correct. Okay, so most of us are saying that the kinetic energy is going to go up, right? What's the direction of the force? To the right, because it's a positive charge. The electric field points to the right. F equals QE. Force is going to point to the right as well. So just focusing on the proton, the field is going to do what sign of work? The work is going to be, if I say the work done by the capacitor or done by the electric field due to the capacitor is F dot delta R, and delta R is from A to B, right? So is the work positive or negative? Work is positive, right? It's pushing in the same direction as the displacement, so it's going to speed up. Delta K is equal to the work, so delta K is greater than 0. So this is, I'm being a little bit loose with the system choice here. This is the system of just the proton. If we then think about the system of the proton plus the capacitor, again, work is just going to be that, or excuse me, the change in potential energy is going to be the negative of that external work. So if the work is greater than 0 in this case, the change in potential energy is less than 0 in this case, right? So delta K plus delta U equals 0. If the kinetic energy increases, the potential energy's got to decrease, okay? So this just looks exactly like which situation we just talked about. The ball, right? Dropping the ball. If you drop the ball or drop whatever, the marker, and let it fall, the gravitational force is in the same direction as the displacement. Kinetic energy goes up, potential energy goes down, okay? We okay here? Questions? Instead of a proton, we now shoot an electron into this capacitor, but the capacitor is still the same, so the electric field direction is still the same. Which is true now? All right, so it's going to be the opposite situation, right? Because the kinetic energy, well, first of all, what's the direction of the force? The direction of the force on the electron is that way, okay? Negative charge times this electric field gives a force in the opposite direction. So as the electron moves from left to right, it's going to be slowing down, right? Kinetic energy will decrease. The work, if the displacement is again from A to B, provided it can get to B, the work, F dot delta R is going to be negative, right, less than 0. And so the change in kinetic energy is less than 0. Change in potential energy is greater than 0 because it's the opposite of that. So we end up again with delta K plus delta U is greater than 0, or excuse me, equal to 0. This is analogous to what? Throwing the ball up in the air, right? So you have a force in the opposite direction of the displacement, okay? So let's actually work this out and calculate the potential energy for each case. So if we said, let's call this displacement delta x. Okay, let's just say it's delta x. So we have a potential energy that's going to be equal to the negative of the work. The work is Fx times delta x, and there are no y and z components in this case. The force itself is the charge times the electric field, x component. There's just an x component here, and that's a positive x component. And the charge, in this case, this is a plus E, the E being the proton charge, E being 1.6 times 10 to the minus 19. So we have a negative E little e times big EX times delta x. Okay, so that's the change in potential energy in this case. In this case, we said the potential energy went down as it moved from left to right. In this case, we have, again, the negative of the work. It's the negative of Fx times delta x, or the negative of Q times E times delta x. But what's the charge now? Negative little e, right? It's the charge of an electron, not a proton. So we have a negative times a negative Ex delta x. So we have a positive E delta Ex delta x. So that's the change in potential energy for the electron versus the proton. So in this case, potential energy goes down. In this case, potential energy goes up. But the expressions look pretty similar, right? I mean, it's just all we're doing is changing the sign. So what if we said, well, okay, if I do it for the proton, it's the negative of a positive E times E sub x delta x. And if I do it for the electron, I could write it this way. I have a negative times a negative E sub x times delta x. So the only thing that's different here is the charge. The E sub x times delta x is the same in both those expressions. So here's sort of the punchline. Just like we've defined electric field to be the force per unit charge, we just divide out the charge and just look at the force per unit charge. In this case, the only difference is the charge, but there's still this negative times an Ex times delta x for both of those cases. So let me look instead at the change in potential energy per unit charge. For the proton, delta U over the charge, which is positive E, is a negative E sub x times delta x. For the electron, delta U over the negative E gives me a negative capital E sub x times delta x. We get the same expression on each side, and that is useful, okay, because now we don't have to care about what particular charge is moving from one point to another. We can just look at two different points, think about the distance between them or the path from one point to another, and say, I know the change in potential energy per unit charge along that path, and then I can apply any charge I want and find what the actual potential energy change would be. Okay, that's the value of what we're going to be doing. And so this thing has a special name. We want to then define a quantity which is the potential or change in potential energy change in electric potential energy per unit charge give it the symbol V. So it's a change in capital V, and that's equal to a change in capital U, electric potential energy, U electric, divided by the charge. And this thing is called the change in just electric potential. Okay. Kind of an unfortunate name. It's not potential energy. It's just potential. And when we say potential, we mean energy per unit charge. Okay? This thing has units of energy divided by charge, so units of joules per coulomb, but there's a special name for that unit. It's called what? It's a volt. This is 1 volt. So when you hear the term voltage, a voltage is a change in energy per unit charge. Okay, it's a coulomb per, or a joule per coulomb. Okay. Note the relationship, though. We now can say that this delta V is the same for both the proton and the electron. It doesn't depend on the charge. It's still going to be negative E sub x times delta x. And so we can write that more generally for, at least for the case of a constant field, for a constant electric field or a uniform electric field. We can relate the change in energy per unit charge, the change in electric potential, to the electric field. It's equal to negative E sub x delta x minus E sub y delta y minus E sub z delta z. But what is that? What kind of product is that? That's a dot product. So we can write delta V is equal to negative of the electric field vector dotted with what we'll call the delta L vector, some path length that has a displacement in the x, y, and z direction. Okay, so these are the basic relationships we're going to be playing with over the next couple of days, and we will do more examples with this next time.